Welcome to this video on Chapter 5, Molecules and Compounds. We will explore how these fundamental building blocks of matter are structured, named, and represented in chemistry. In this video, we will cover key topics such as constant composition, chemical formulas, naming conventions for various types of compounds, and how to calculate formula mass. Our learning objectives focus on naming ionic compounds, molecular compounds, and acids, as well as mastering the calculation of formula mass for different chemical substances. We will also learn to apply the law of constant composition, write chemical formulas, classify elements and compounds, and determine the number of atoms in a formula. Did you know that the properties of a compound can differ drastically from the elements that compose it? Take table sugar, or sucrose for example. It is made of carbon, hydrogen, and oxygen, yet its properties are completely unique compared to those elements on their own. Consider table salt, sodium chloride. Sodium is a highly reactive metal that dulls quickly in air, and chlorine is a poisonous reactive gas. Yet, when combined, they form something we use every day. Sodium chloride is the result of combining these two elements. This illustrates a fundamental chemical principle. The properties of a compound are generally quite different from the elements that compose it. Most substances we encounter are compounds, not pure elements, as free atoms are rare in nature. Unlike a mixture, where proportions can vary, elements in a compound combine in fixed, definite proportions. This slide contrasts a mixture of gases in a balloon with a chemical compound like water. In a mixture, ratios are variable. In a compound like water, the ratio of hydrogen to oxygen is fixed. Joseph Proust formalized this observation as the law of constant composition. It states that all samples of a given compound have the same proportions of their constituent elements. For instance, if we decompose 18 grams of water, we consistently get 16 grams of oxygen and 2 grams of hydrogen, resulting in an oxygen to hydrogen mass ratio of 8:1. Similarly, ammonia displays a constant mass ratio between nitrogen and hydrogen. While atoms combine in whole number ratios, it is important to note that their mass ratios are not always whole numbers. Chemical formulas allow us to represent these compounds. An example is H2O, which indicates that water is made of hydrogen and oxygen in a 2:1 atomic ratio. When looking at a chemical formula, remember that subscripts indicate the number of atoms. By convention, if there is only one atom of an element, the subscript one is omitted. Common examples of formulas include sodium chloride for salt, CO2 for carbon dioxide, and C12H22O11 for sucrose. These subscripts represent fixed relative numbers of atoms that define the specific compound. Moving on to our next point. Changing a subscript in a chemical formula creates a completely different compound. For example, Colorado is carbon monoxide, which is a harmful air pollutant. If you change the subscript of oxygen to 2, you get carbon dioxide, which is relatively harmless. When listing elements in a chemical formula, we follow specific rules. We generally list the most metallic element first. For example, we write sodium chloride as sodium chloride, not ClNa. For non-metal compounds, we list the more metal-like element first, which is typically towards the left or bottom of the periodic table. The specific order for listing non-metal elements is established by convention, as seen in this table. While there are some historical exceptions, such as the hydroxide ion written as OH-, adhering to this standard order helps maintain clarity and consistency across chemical nomenclature. Some compounds contain polyatomic ions, which are groups of atoms that function as a single unit. When more than one of these groups is present, we use parentheses followed by a subscript to indicate the count. To find the total number of atoms, simply multiply the outside subscript by the one inside. Here is an example using magnesium nitrate, MgNO32. This formula indicates one magnesium atom and 2 nitrate groups. By distributing the subscript of 2, we can determine the exact count of each atom: 1 magnesium, 2 nitrogen, and 6 oxygen atoms. Chemists use various types of chemical formulas. An empirical formula shows the relative number of atoms, while a molecular formula provides the actual number. A structural formula goes further, by using lines to represent chemical bonds and showing the connectivity between atoms within a molecule. To help us visualize molecules, we use three-dimensional molecular models. Ball and stick models use spheres and rods to depict atoms and bonds, while space-filling models show how atoms occupy space. These models are color-coded to distinguish different elements. Let's look at methane, CH4, as an example. Its molecular formula identifies the atoms, its structural formula shows their connections, and the models help us understand the three-dimensional geometry, illustrating how the hydrogen atoms are arranged around the central carbon atom. These various representations help bridge the gap between our macroscopic observations and the microscopic world of atoms. By connecting what we see in the physical world to symbolic representations, we gain a deeper understanding of molecular structures. Pure substances are classified into elements and compounds. Elements can exist as isolated atoms or as molecules, while compounds are either molecular or ionic in nature. This classification is fundamental to understanding how substances behave. This flowchart provides a clear overview of how elements and compounds are classified. It visually maps out the breakdown from pure substances to atomic or molecular elements, and from there to molecular or ionic compounds. Atomic elements consist of single atoms as their basic units, which includes most elements on the periodic table. Conversely, molecular elements typically do not exist as single atoms in nature, but instead as diatomic molecules where two atoms of the same element are bonded together. On the left, we see an atomic element, mercury, represented by single atoms. On the right, we see a molecular element, chlorine, existing as diatomic molecules. This visual comparison highlights the difference between these two ways elements can be structured. Certain elements naturally exist as diatomic molecules. These include common gases like hydrogen, nitrogen, oxygen, fluorine, and chlorine, as well as bromine and iodine. Remembering these elements is key to understanding how they react and combine with others. Finally, compounds are classified as either molecular or ionic. Molecular compounds are composed of non-metals forming molecules. Ionic compounds contain cations, usually metals, paired with anions, usually non-metals. Recognizing these types is essential for predicting the chemical properties of a compound. Compounds can be either molecular or ionic. For instance, the basic units of dry ice, which is a molecular compound, are carbon dioxide molecules. In contrast, table salt is an ionic compound composed of sodium chloride formula units. Ionic compounds form when a metal and a nonmetal combine. The metal loses electrons to become a cation, while the nonmetal gains them to become an anion. These ions are then held together by their attraction to form a three-dimensional array, rather than discrete molecules. When writing formulas for ionic compounds, remember that they must be electrically neutral. This means the sum of the charges of the positive cations must exactly equal the sum of the charges of the negative anions. To write a formula, place the metal symbol first, followed by the nonmetal. Use the magnitude of the charge of one ion as the subscript for the other. Finally, reduce these subscripts to the smallest whole number ratio, ensuring the total charges cancel out. Let's apply this method. When aluminum with a 3+ charge combines with oxygen with a 2- charge, we swap the numbers to get aluminium oxide. For magnesium and oxygen, both have a magnitude of 2, so the charges cancel, resulting in MgO. Some compounds involve polyatomic ions, which are groups of atoms that act as a single unit. It is important to familiarize yourself with these common polyatomic ions to recognize them easily when reading chemical formulas. Nomenclature is the system for naming chemical compounds. While many substances have common names, like water for H2O, scientists use systematic names such as dihydrogen monoxide. Common names rely on familiarity, whereas systematic names follow specific, learnable rules. To name an ionic compound, start by identifying it as ionic. You can generally assume a compound is ionic if it contains a metal and one or more nonmetals. Ionic compounds are categorized by the metal they contain. This flowchart illustrates the process of identifying the type of ionic compound, which determines the naming convention used. We classify these into two types. Type 1 metals have an invariant charge, meaning it doesn't change. Type 2 metals have variable charges and are typically found among the transition metals. Note that some exceptions exist, like zinc and silver, which maintain constant charges. This slide displays various metals that have an invariant charge. Recognizing these is the first step in correctly naming binary ionic compounds. Conversely, here are some common metals that form more than one type of ion. Because these metals can have different charges, their specific charge must be indicated when naming the compound. Binary ionic compounds consist of only two different elements. Since the charge of a type 1 metal is invariant, you don't need to specify the charge in the name. You simply combine the name of the metal cation and the base name of the nonmetal anion with an IDA ending. For example, sodium chloride is named sodium chloride. We take the name sodium for the cation and chlor for the anion, adding the ID suffix to finish the name. Finally, this table lists some common anions. Knowing the base names for these nonmetals and their typical charges will help you accurately construct and name many binary ionic compounds.